Hi, I'm Yassine Barhoumi. Thanks for inviting me to the MIDL 2021 conference. I'm a PhD student at Rowan University, working on vision transformers and their application. And today, I'm presenting my multi-CNN vision transformer hybrid model called Scopeformer and its application to the RSNA hemorrhage classification challenge. So the input to our architecture is an RGB image that we input into a CNN in order to extract high-level features with a dimension set priorly to 7 by 7 by 1024. So we do the same thing for all the CNNs put in parallel and extract high-level specific features to each CNN with an identical dimension of 7 by 7 by 1024. Note that the height and width must be similar in order to concatenate them later, but the number of channels can vary. In our case, we did not change the number of channels, so we can compare these features against each other's using the cosine similarity metric. And the CNN that we used was an Xception CNN, and we did not vary that also, so we can highlight the pre-training paradigm that we used for each CNN and their contribution to the overall and feature richness feature richness to the Scopeformer architecture. So next we concatenate these features along the third axis along the depth, and we get a feature map with a dimension of 7 by 7 by n times 1024. Of course, tokenization or patch extraction to get these the patches, and each patch is the dimension of each patch is 1 by 1, and of course the number of channels is conserved. We do the same thing for all the patches, and we get 49 patches, and then along to the CLS token and the positional encoding, we get 49 plus 1 input vectors to the vision transformer encoders. So we have 50 vectors, whereas if you're using the raw images and using a patch size of 16 by 16, we get the input vectors will be number of input vectors will be 197, and in our case is 50, which enables some computations gained. However, the number of channels in our case is larger. So we input these tokens or vectors into the ViT encoders, and then the MLP head, and then we derive the classification. So we use two types of datasets for pre-training. So the first one was ImageNet, and the second was data was generated using style transfer method applied on also ImageNet. So basically, we take an image, we set the target to be an MRI head scan or picture, and the output will be a side transferred ImageNet picture. So we do this using multiple targets in order to unbias the model towards these specific pictures, and we're doing this method in order to enhance the or improve the bias towards these the textures or the shapes of this brain images, and thus improve the classification. So the training dataset was the RSNA derived from the DICOM files, that we applied a standard 3 windows techniques in order to derive these JPEG formats. So for the results, as we can see, I'm using a hybrid model is better than vision transformer, and by roughly 1.5%, and then from there, the more we add CNNs, the more we add feature extractors, the more we have a better classifications all along until 3 CNN vision transformer. And another observation that we have here is the more that you vary the pre-training paradigm for your CNNs, the more that you have classifications. Thank you.